Well, here we go for the second lecturette for Astronomy Laboratory. Last time, what we talked about is on experiment number 7, which is Kepler's Law, how you're going to go ahead and plot some data for an orbiting satellite that's going around the moon. And the reason why we're doing this is simply this reason. For a long time, especially from the Greeks on, in ancient Greeks, the idea of the universe was that the earth was the center of everything and everything moved around us. And for the Greeks, they were an amazing mathematicians. They perceived the universe as being perfect outside the earth. And for them, the realm of the perfect meant perfect circles. So imagine this. Here is the earth, and then all the solar system objects, that means the moon, the sun, and the planets would move around us in different types of orbits, but they were all circular, centered on the Earth. But there's a problem there. And the basics of this problem is that you need to be able to make predictions based upon the model that you have. And if the predictions don't come true, then that model's not good. If they do come true, then it is a good model on the reality of what the universe is like. So if the Earth is in the center of things and the planets moved around us according to those ancient models, they should be able to make a prediction on where the planet will be in a month's time when you see it tonight. And again, it's all based on the model. And so you look in a month's time, and if that planet happens to be where you expect it to be, where you predicted it to be, then that model said it would be good. And guess what? It wasn't the case. It wasn't that great a model. And so that began this effort that lasted thousands of years, trying to understand how things are positioned in the heavens, where the Earth is relative to everything else, and how do things move. So it's a long story. This is the laboratory section, and so the issue here is, let's jump to kind of the 1600s in that time frame. And the idea is that there were measurements made of where the positions of the planets were as seen from the Earth by Tycho Brahe, a Danish astronomer. And his measurements were extremely well coordinated, well made, and he listed that against time. He wanted to use those recordings of planetary positions to determine exactly what the motions of the planets are. And that began a math problem that lasted 20 years to try to solve. And the man who solved that was a great mathematician by the name of Kepler, Johannes Kepler. And remember, the idea was, number one, the predictions didn't come true. Number two, the orbits were thought to be perfect circles. And what Kepler found is 3 laws of planetary motion. And those 3 laws will be verified by you and me using the data of a satellite that was placed up and orbited the moon. And so this is the data that you have in your lab textbook. See the page number. And you're going to be plotting this. So let me remind you what you did. And let's go back and look at this graph that I made of this data. So I made this graph a little darker, so hopefully it's a little bit easier to see. And so what we have here, first off, is that this right here would be the position of the moon. And we count the radius of the moon to go from the center origin of the XY axis. So that's where the center of the moon is. And we count out 5 of the grid marks, 1, 2, 3, 4, 5, and we give that a unit of 1. And we go the other way, 1, 2, 3, 4, 5, that's a -1, again, because we relate it to that origin of the XY axis. So here is the x-axis. There is the y-axis that we make. And what we do is we count out 5 grid marks to get 1, 5 more grid marks to get 2, and so forth. 5 grid marks to get -1, 5 more grid marks to get -2, -3, -4, and then we go -1 minus as far as we can down here on Y, and then 5 grid marks for 1, 2, 3, 4, 5, and 6 up here. And what we do is we look at that data, and what we see, let's look at the very first one where it says time equal to 0. And what we see is a value of x and y. And what the value is for x is 3.62, where each of those units is related to the radius of the moon. So I would count, again, for x is minus 3.62 from table 1. So I would count out -1, -2, -3, and 0.2, 0.4, 0.6, slightly more than that. And then it says y is 1.04. So I go up here to 1.04 and I make a mark. And I do that slowly but surely all the way around. So you see all the different marks I made from the data. And then I connected them with a smooth line to make the orbit of the satellite. So this is the orbit of the satellite around the moon, and there's the moon right there. And so that's the very first thing you have to do. And so obviously the orbit of that satellite is not a perfect circle. In fact, it's what's known as an ellipse. It's an elliptical orbit. So we're going to explore this. And so Kepler discovered something new from the data of Tycho Brahe, that planetary motions, or any motions for that matter, of anything orbiting another object is not circular, is typically elliptical. So, first thing you do is, if you look at your book, the first page, read that, and the second page, read the top of it, and then answer the 2 questions on page 84. And then what we need to do is to be able to look at those definitions and walk through what those definitions are. And those definitions are frankly related to a lot of the ideas of the geometry of ellipses. So what I'm going to do in the purpose of this lab experiment discussion or lecturette is to go through the geometry of the ellipse, because you need to do this. And as I go through that definition, what you'll determine are things that you can answer the definitions for. Once I go through those definitions for the different geometric parts of an ellipse that you have to be worried about, then what we'll do on the next lecturette is we'll use the actual graph that you make from the data to determine some of those geometric figures and ideas for the orbit of the satellite. So here's the geometry of an ellipse. And so it looks like a squash circle. Okay, so that's an ellipse. So the satellite's always going to be found somewhere within that. So that is the actual orbit that whatever is orbiting is going along. It's never found outside that orbit. It's never found on the inside of that orbit. It's always found somewhere in that. So I'm going to define some things that you always find with ellipses. Now, if you take 3rd semester calculus, you'll learn a lot more about this stuff than what I'm going to give you, but that's not what we need here. This is for a beginning basic astronomy laboratory and talking about Kepler's 3 laws of planetary motion. So in all ellipses, we always have 2 special spaces, right there and right there. Well, let me actually do a little bit better job. Let me try to be somewhat symmetric here. And these things are known as a focus. And notice that there are 2 foci. Focus is a singular. Foci is plural. And there's always 2 of them found within an ellipse. And so what we know is that the moon is generally, or a planet, or whatever is being orbited, is generally centered on one of the foci. Now, there's some slight variations of that because of some discoveries of Isaac Newton, but we'll kind of neglect that for right now, so don't worry about that. So let's define a few things. If I would draw through the two foci, let me kind of do a better job. You know my drawing, guys. It's really crappy. So when I draw a line that passes through the two foci, if it was drawn correctly, this half should look exactly like that half. We say it looks symmetric. And what that line does, number one, it passes through both foci. And number two, it cuts it into two equal halves along the long axis. And we call that long axis the major axis. If I don't have a moment there, the major axis. And it cuts it in the long axis. Now, if I can find a halfway spot, I could draw another axis that cuts it, should be equally symmetric this way, back and forth. This half should fold over and exactly match that half if I was a good drawer. And of course, I'm not. And so this is what's known as a minor axis. And again, it cuts it in the ellipse, the shape here, into two equal halves along the small axis of this. Now we have a symbol that represents basically the lengths of this. So the length of this is about a foot, but we call the length of the major axis 2a. So in this case, 2a would equal about a foot on this particular drawing. For planets, 2a for the major axis for a planet, it might be, millions, if not hundreds of millions of miles, depending upon the planet. And the length of the minor axis is 2b. And there's just a way to, in a symbolic way, to represent those numbers. Now there's another length that we're interested in. And what that is the length between the two foci. We call that length just simply 2d. Now, know something. See if I have another colored pen here. I don't think I do. This is all symmetric. So this length right here should be d. And that length, if I could draw correctly, would be d also. That should be b, and that should be b, and that should be a, and that should be a. So it's a little messy, so let me redraw this again so that it's a little clearer. There's always two foci. We have a major and minor axes, and then there's a distance between them. So I'm going to draw this one more time. You draw this a few times, you get finally good at drawing potatoes because it seems like a potato shape, doesn't it? Remember I'm from Idaho. So let's go ahead and let's look at this. So again, here is my elliptical shape. Here is one focus. Here is the second focus right here. If I draw a line through both foci, that makes what is known as the major axis. And remember, it has a length of what? 2a. And then if I carefully draw through the center and at right angles to the major axis, another line, so this is at right angles to this one. This turns out to be the minor axis. And again, the length is 2b. So this length from there, from the center over to the edge is a. From the center over there is a. From the center there up to the curve is b, and b down to there for the minor axes. And then the final thing we said is that the distance between the two foci is 2d, where that distance is d and that distance is d, because of the symmetry of these things. So, what we see here then are some things that you can answer some of the questions and some of the definitions that's in your book. And so you should proceed working on that. So what we find, the definitions are found again on page 84, 85, and 86. Now we haven't given everything that you need for this, but certainly we have quite a bit here. Now, go ahead and you can feel free to look at a radius. If we have a circular orbit, then if I have the center of a circle, then a line going out to the edge of the circle, that's known as the radius. And so we see that. You can, some of the definitions you can just go ahead and draw and define it by the drawing. Whatever makes it clear to you. Now, so we have these things that we need to know. Let's see, where are we at? Just looking over here. So we can, again, answer the questions on page 84. We can start working on the definitions on page 84. And let's see, minor axis. So there is one other thing regarding the geometry of this. So let's go ahead and let's look at this. With geometry, ellipses can be quite circular looking, and they can be quite drawn out, kind of stretched out like that. And so there must be something that will basically define to us in a mathematical way just how squashed and squished that circle is, you know, down into an ellipse. Not very much and quite a bit. And what measures that is something called eccentricity. Fancy word, we just call it E. And so for an ellipse, this is how we define it. The ellipse is equal, the eccentricity is equal to the distance between the foci, that's equal to 2d, divided by the length of the major axis. So that's divided by 2a. Leave the 2's there, even though, of course, they would factor out, just to keep in fact that it's this distance divided by that distance. And notice something, guys. If I have a small distance, let's say it's 5 feet, and I divide it by a big distance, 10 feet. Number one, the feet goes away. The unit goes away. Same thing if it was meters. If it was 2 meters divided by 5 meters, well, the meters are canceled. And so this thing called eccentricity is unitless. And it gives us some idea of how it's been squished. So, look at this. For this guy, it's a small distance divided by a big distance, so 2 divided by 5. Notice this, that it's less than 1. So the eccentricity of an ellipse is less than 1. And so imagine this. Let's see if I can actually get you to use your mind's eye. Imagine I have a circle. It's made out of metal. And you see the radius right in the center. The center of the circle right there. And the radius would come out in the other side, and so you get a diameter. So what I'm saying is, imagine that you have a piece of metal, and right there is the center of the circle. So this is a circle. And then you have 2 times the radius, which is the diameter of that. And let's imagine I could take this, and as I squeeze it, that point, which is the center, begins to pull apart. And the more I squeeze it, the further apart that center breaks into 2 and moves further and further apart. And so the more squeezed it is, the further this goes, the less squeeze it is, the closer those foci get together until finally, if I don't squeeze, they'd be on top of one another and would be a circle. If that's not clear, go back and listen to that. So again, what happens here then is that kind of gives you a sense of how squished that is compared to this. And so it turns out that for the ellipse, the eccentricity falls between 0 and 1, but does not include those two numbers. So let's think about this. For a circle, let's imagine that the diameter is the major axis. And the distance between the 2 points now are on top of one another, so the distance is 0 between the 2 points that make up our foci eventually. So really the eccentricity of a circle is 0 divided by the diameter of that circle, which is 0. So this certainly will not have a eccentricity of 0 because it is an ellipse, but it's going to be very close. But the more I put that apart, squeeze that, the farther those foci are, and so that distance will be greater and greater until finally they approach what the major axis is, and it'll get closer and closer to 1. So guys, if I have an ellipse that looks like that, will it be closer to 1 or 0? And so it turns out that it would approach 0. This one is, again, is it going to be closer to 1 or 0? No, it's going to be closer to 1. Not going to be equal, because ellipses are never equal to 1, never equal to 0. So, what can you answer right now? You can answer some of the definitions all the way up to E. We have more to talk about after that. You can also talk about radius on H. You can go ahead and answer the questions on page 87 and top of 88. And then what we'll do is when we get to data graphing, I'll go ahead and place this information that you need there on the lecturette number 3. So let's kind of recap this for a moment. Number 1, you have a bunch of data on table 1 for an orbiting satellite moving around the moon. You use that to graph, again, this. And the trick here is first off placing your XY coordinate system there. And then you go carefully step by step, putting a plot in, and then eventually connecting this, and that would be the orbit of the satellite. The moon itself is centered on the origin of the XY axis, where there's a value of 0, and the radius goes from 0 out to 5, 0 out to 5, 0 out to 5, and so forth, as far as the grid little units. We call that 1, 2, and so forth. And that's how you utilize that data on table 1. Just to be clear, this is where I placed my origin, where the X and Y axis cross. If I go up from here, I go 1, 2, 3, 4, 5, 6, 7, 8, 9 up. And if I go from here along the x-axis, that's along the y-axis. Along the x-axis, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that's where I have my origin and the x and y-axis cross. And just use a ruler to draw that axis. Don't use it by freehand. And make certain that you use a pencil to graph this in case you make a mistake. So it'll be very easy to make a mistake. That's all right. Took me a while to graph this to be where it was represented what the data was. And so if it's going to take me a while, certainly will take you a while because I've obviously done this many times in the past. Maybe not so often for you. And that's all right. Take your time. Do a good job. You can see what it looks like. It's not squashed in. It's not squashed in. It flows pretty equally. So if you got a part that's really squashed in, relook at those data points where it's squashed in, let's say, and maybe you made an error where you placed things. Just take your time. Use a pencil. Remember, these graph sheets are found in Appendix 7 in the back of your book. And so just take your time, put in the moon, put in your data points, and then attach this. What's next? We take this and we utilize this to find the major and minor axes. We find the placement of the second focus, because remember, one focus will be the origin, because whatever's being orbited is centered on a focus. We said that earlier. And so a lot of details. I wish I was there with you to be able to help you. But remember, I'm checking my email continuously, and I am available to aid you, and be patient. Also, I do hope to have a Zell session sometime in the next week so that we can talk. We're going to take plenty of time to do this. This is an important lab, and I want you to understand it. Take your time. If you have phone numbers of your group members, please feel free to talk to them. I want you to know that collaboration is fine, just don't copy. Do your own work, but helping one another is a good way of maintaining contact with one another, having someone to talk to, having someone to help you if you don't fully understand it. And we will then work together, because I'm available for that too. So that's the lecture number 2. Now a little announcement for the lab exam. I believe we'll have a lab exam over the first half of the material in probably 2 weeks. And so I will do a little review lecturette on the material that we've talked about, and we did a bit of a review before. So go through and start looking over your labs, read the material that we've been through, look at your notes, talk to your lab mates, and of course talk to me too. I'm right here available to aid you. And what we'll do then is I'll find a means using Canvas or something to get your exam to you. Make certain that if you had problems with experiment number 6 because of your data, there was a group that did, remember, you're supposed to let me know, and I will give you some data to work with so that you can proceed with this. And I'll give you plenty of time to do this. Main thing is I want you to understand what's going on here. Obviously, on exam 1, this experiment number 7 will not be on it. And so I'll go through that review with you. Again, for those who are the ones that, like I just mentioned, that's having difficulties because of data collection problems, I'll get that data out to you this weekend so that you have plenty of time to do the analysis. And again, let me help you if you get stuck, and help one another. Contact one another, okay? If you know of anyone that's not online at the Facebook group, Prof. Astro Mike, CC Astronomy, please have them sign in. Keep an eye at the Canvas site. Keep an eye on your email. And let's make sure that we work together. So what should you be doing? Number 1, get this graphed. It takes some time. Number 2, use the graph paper in Appendix 7 and graph it with a pencil. Place your XY coordinate system there. Remember, I've told you the location of the origin just a moment ago. And remember, you count out 1, 2, 3, 4, 5 to give 1 unit on the axis. And then 1, 2, 3, 4, 5, and 2 units, and so forth. Obviously, this is going to be minus. That's going to be positive. That'll be positive, and that'll be minus as far as the units on the axis. Take your time. Let's see if I can make this a little bit closer so it gives you a chance to be able to see it a little bit better. Okay. So notice how things are listed there. And notice how I've got data points in there and I plotted it. Notice how the graph looks. Notice where the moon is. Look at the location of the origin for the X and Y axes. And just take your time. You can pause the video here and make certain that you've got things in agreement. Now, it may take more than one sheet of the graph paper where you might have to tape it together. And if so, just be aware that you don't want you want things to be lined up properly. If you have to line up, the couple of graph papers, go ahead and take a look at that and see what you need to do. Guys, I hope I'm being helpful. I hope I'm being clear. My heart's with you. I wish that there was things that we could do better, like being together in the classroom. Isn't that what we want? But we will make it through the best we can. I am here. We have many ways of communicating. Please communicate if you need anything from me. Talk with you with lab lecture number 3 very soon as we proceed using this graph to find things like major axes, minor axes, and the placement of focal points. Of focuses, I'm sorry. Anyway, talk with you soon. Bye-bye.